our last speaker. So we've got Giacomo Mezzedimi, who's going to talk about the Kodaira dimension of some moduli spaces of elliptic K3 surfaces.
Yeah, thank you very much. And let me thank all the organizers for giving me the chance to talking here at the GAEL today. And yeah, exactly. I'll talk a little bit about the Kodaira dimension of some moduli spaces of elliptic K3 surfaces. I hope you can hear me well and you can see the slides. So let me start by saying that this is a series of joint works. So the original project started with Mauro Fortuna, and it led to a result that I'll introduce at some point. And then we got in another direction, thanks also to Michael Hoff. And I hope I'll talk a little bit at the end about the recent developments about this stuff. It's still kind of a work in progress. So we will work over the complex numbers, and in the first part of the talk, I'd like to introduce you a little bit the objects that I want to study. And the first object that we introduce, I'm sure many of you already know this, but is K3 surfaces. So K3 surfaces are surfaces that have a trivial canonical bundle. And we know that in dimension 2, there are either K3 surfaces or abelian surfaces. And well, by saying that we want them simply connected, we just exclude abelian surfaces. And the canonical bundle is trivial, so there exists an over-vanishing holomorphic two form that we denote normally by omega x. And let me just say that we can think of K3 surfaces on some sort of generalization in dimension 2 of elliptic curves, since elliptic curves has exactly a trivial canonical bundle. And so there will be some connections between K3 surfaces and elliptic curves that we'll try to exploit. So let me give you some very usual examples of K3 surfaces. We have smooth quartics in P3, like maybe the most famous example is the Fermat quartic, but still very famous are kind of complete intersections in P4 and P5. And for K3 surfaces, these are complete intersections of a quadric and a cubic in P4, and complete intersections of 3 quadrics in P5. So an object that we usually attach to K3 surfaces, and it's an object of really great interest, it's the Néron-Severi lattice, which is an object of linear algebra. So as a group, it's simply the Picard group, for instance, or the Néron-Severi group. And we view it inside the second cohomology group with integral coefficients. But of course, we have an intersection pairing on the surface that defines a bilinear product on, let's say, on the H2. And well, we can study what kind of bilinear product this is. Well, first of all, it turns out if X is a K3 surface, its second cohomology group with integral coefficients is a free Z module of rank 22. And the intersection pairing on it makes it isomorphic to a specific lattice. So with lattice, I will mean in the talk just a free Z group with a non-degenerate and even bilinear pairing. So non-degenerate just means that there are no isotropic subspaces, and even just means, so not isotropic, so basically non-degenerate means that the extension to the real bilinear product is non-degenerate. And also even meaning that all self-intersections are even. This is just true for K3 surfaces. And actually, we know the shape of this bilinear product is just always isometric to the following lattice. So we have 3 copies of the hyperbolic plane, which is simply the rank 2 lattice with the following intersection pairing. And then we have 2 copies of this E8 minus 1. This is a certain negative definite lattice of rank 8 that arises from linking diagrams. It's not so important to know what it is. It's just a very nice negative definite rank 8 lattice. And of course, this about the H2, but we can look about at the Néron-Severi lattice inside of this H2, and this will be still non-degenerate and even. And we also know that its signature is, so it's hyperbolic. So its signature has only one dimensional positive part, and this is because of the Hodge index. So let me give you an example how we think about Néron-Severi lattices on K3 surfaces. So for instance, let's consider the examples that we had before. Like let's focus on a quartic in P3. Well, of course, if we have a quartic in P3, we have the hyperplane section H that is a certain element in the Néron-Severi group of the K3 surface. And the self-intersection is just the degree of the surface, so 4. And well, we can rephrase this in a much, different way that will be more convenient for us. And we can say that there exists an embedding of lattices like this. Now I'll explain what I mean by this. So by this 4, I mean just the rank 1 lattice spanned by one vector of self-intersection 4. And with this arrow, I mean that there exists an embedding, so an injective map of groups that preserves the bilinear pair. And well, what is the advantage of this? Well, we have basically rephrased a geometric property of the K3 surface, so being a quartic in P3, into some sort of linear algebra property of the Néron-Severi lattice. And our goal will be kind of to reverse this line of reasoning. Like if we have an embedding like this, can we say that the K3 surface is a quartic in P3? And well, for this, we will need moduli spaces. But before going to moduli spaces, stop me at any point if you want to ask questions. Just feel free. Stop me anytime. So before going to moduli spaces, let me just introduce elliptic fibrations and elliptic K3 surfaces. So we will say that K3 surface is elliptic if it admits an elliptic fibration. An elliptic fibration is just a fibration in curves of genus 1 with a section. So let me give you maybe a picture for whatever this can mean. So we have a K3 surface X that has a map to P1. And the fibers are, well, almost all the fibers are smooth elliptic curves. But of course, we can have nodal rational curves, we can have cusps, and we can actually have some reducible fibers like this, or there's a classification of the singular fibers. But you should think of elliptic fibration something like this. Some disjoint elliptic curves or degenerational elliptic curves going, spanning the K3 surface. And of course, a zero section. A section is just a smooth rational curve that intersects all the fibers at one smooth point. So okay, that's the geometric picture. What does this imply at the level of the Néron-Severi group? Well, we have two classes now, two curve classes, the class of the fiber and the class of the zero section. And we can compute their self-intersection by using Riemann-Roch. And we see that any smooth curve of genus 1 has self-intersection 0. And any smooth rational curve has self-intersection -2. So since these two curves meet at one point, the intersection pairing is as follows. So it's this 2 by 2 matrix that we can see in a very, very straightforward way, being isomorphic to the hyperbolic plane. So the idea here is very similar than before. So we start with a very geometric intrinsic property of the K3 surface. The K3 surface admits an elliptic fibration. And we're rephrasing it in terms of an embedding of lattices. In particular, we want the Néron-Severi group of the surface to contain a copy of the hyperbolic. So after this, I hope it doesn't come as a surprise, the following definition. So let me fix M to be an even non-degenerate hyperbolic lattice embedding primitively into the K3 lattice. So that's a lot of words, but so even non-degenerate hyperbolic, these are just the properties of the Néron-Severi lattice. So you can think as M as a candidate Néron-Severi lattice of K3 surfaces. And we want this embedding to be primitive. Primitive is just a technical assumption that we need for embedding of lattices, kind of a crucial hypothesis. It simply means that the co-kernel of the embedding has no torsion. But it's just a technical assumption. And then we can say that an M-polarized K3 surface is a pair made of K3 surface X and an embedding J of this fixed lattice M into the Néron-Severi of the K3 surface. We also want the image to contain a big enough divisor. This is again a technical assumption, but the core of the definition says that an M-polarized K3 surface is simply a K3 surface whose Néron-Severi lattice contains a copy of this lattice M. So it gives some information about the curve classes on the K3 surface. And well, now we want to construct the moduli spaces of these objects that turn out to be very, very well behaved. So what we do is the following. We fix an M-polarized K3 surface, and we consider the orthogonal complement of the lattice M into the K3 lattice. So it's this big 22-dimensional lattice that is the lattice of the K3 surface. And of course, we can look at the holomorphic two forms that trivializes the canonical bundle, and this will be a point in the following period domain. So we look at this orthogonal complement and we complexify it, and then we take the projectivization of this. So the holomorphic two form will be a point here, and actually the period satisfies the following two equations. So it has self-intersection 0 and it has positive intersection with its complex conjugate. And if you look at this period domain, well, this actually has two sheets. It's like the two sheets of a hyperboloid. So this plus just means that we choose one sheet. And of course, there's a group acting on this period domain, and it's the following nice group. It's the group of isometries of this big K3 lattice that preserve this decomposition in sheets and that act trivially on our lattice M, because we want our fixed part M to be preserved by these isometries. And well, the Torelli theorem for lattice polarized K3 surfaces says precisely that the quotient of the period domain by this group, it's just the coarse moduli space of M polarized K3 surfaces. So points of this quotient correspond to K3 surfaces whose Néron-Severi lattice contain a copy of this lattice M. And well, okay, we have proved the existence of this moduli space, but well, we have more than that. This moduli space is very, very well behaved. It's just a quasi-projective variety. And this follows by the Bailey-Borel compactification that gives a precise compactification of this space. So it's a very, very well behaved space, and we want to study its properties. And maybe one of the first things that one wants to understand about these moduli spaces are their birational type. And by this I mean, so for us, it will be mostly interesting to ask ourselves whether these moduli spaces are unirational. So let me recall that a space, a variety, is unirational if there exists a dominant rational map from a projective space to, in this case, the moduli space. And why is this fundamental? Well, if you can prove that a moduli space is unirational, you're basically able to parameterize explicitly all its objects. Let me give you an example. Like, for instance, let's consider the moduli space F4. So this is the moduli space of 4 polarized K3 surfaces. So K3 surfaces that admit a big NF vector of square 4. Well, it turns out that the general element of this moduli space is just a quartic in P3. Basically, this element of square 4 is big enough. If you ask that it's very ample, it will define an embedding of the surface into P3. And so it will be a quartic surface. And it's a general property that this is very ample. So actually, the general element is a quartic in P3. And this means that there exists a dominant rational map from quartics in P3 to this moduli space, just attaching to every quartic surface the isomorphism class, to every smooth quartic surface, the isomorphism class of itself. So this F4 is unirational, and well, we have provided a parametrization of its elements. They're just quartics in P3, and that's a big deal. And we would like to do this for many other moduli spaces of K3 surfaces. But of course, unirational moduli spaces are very rare. And so for many of them, we want to prove that they are not unirational. And the way we do this is proving that they are of general type. Actually, this says a lot more. It says that they have maximal Kodaira dimension. So sections of the pluricanonical bundle grow as fast as they can. And so they're not unirational. And so that's what we want to study. And this kind of questions is classical in the literature. Most of the work has been done about this moduli space F2D. So these are the moduli space of 2D polarized K3 surfaces. So K3 surfaces of degree 2D, basically. And they were studied, they were studied since a long time, but Gritsenko, Ulek, and Sankaran proved that these moduli space are of general type if D is big enough. In this case, big enough, it means that it's at least 62. And they have information about these moduli spaces also for smaller values of D. And on the other side of the spectrum, we know by classical works and also recent works that this moduli space F2D is unirational for small d, where small in this case means d at most 13, and for the following other values of d. And this is recent work. So it was classical work by Mukai and recent work by Farkas and Verra and many other people. And the last known result that I want to mention, because will be the moduli space we're mostly interested about, is the moduli space of elliptic K3 surfaces. So you can think of this as the moduli space of U-polarized K3 surfaces. So K3 surfaces whose Néron severity contains a copy of the hyperbolic plane. And this moduli space is rational. And I mentioned this again because it's the moduli space we'll be interested in, but also because it's one of the few moduli space of K3 surfaces that we actually know being rational, not only unirational. Okay, so let me come to our results. And our goal is to study the following moduli spaces. The moduli spaces that we denote by M2K of U plus minus 2K polarized K3 surfaces. So first of all, these are 17-dimensional spaces, and they are divisors into this rational space of elliptic K3 surfaces, because this has rank 3 as a lattice, so one more goes in codimension, one more.
I'm sorry, can I ask a question? What is the argument for proving rationality of the moduli space? Is it can be in,
Sorry, can you repeat the question? I didn't hear that.
If I can ask you, what is the argument for showing rationality of the?
Yes. Okay. Okay. So unirationality follows from bias class vibrations. So you can basically write every elliptic surface as a bias class vibration, something like y squared equals x to the third plus a certain polynomial x plus b, and this shows unirationality because the choices of a and b are polynomials, so the choice is rational. And to show that it's rational, it's actually a funny argument, and this is due to Lejarraga, and it uses some sort of trick, I think invented by Dolkechev, in which they show that there is some sort of section of this moduli space with specific properties, and they deduce rationality. It's a very, very clever argument, and the paper is like not even one page. So if you want more information, I'd be happy to give them.
Thank you very much. Thank you.
Yeah. Other questions or curiosities? Okay, so we want to study these moduli spaces. So again, these are divisors into this rational variety, and we want to understand their birational type. So how is it hard to parameterize their objects? And the question is interesting because we have a very, very clear geometric interpretation of these K3 surfaces. So first of all, they contain a copy of the hyperbolic plane, so they're elliptic. So they admit an elliptic vibration. But there exists an extra curve class, and this K contains a lot of geometric information. For instance, if K is 1, the general K3 surface in this moduli space has the following picture. So there exists an elliptic vibration. Again, almost all the fibers are smooth. There are some nodes, maybe some cusps. But for sure, there exists at least one reducible fiber. And in the very general case, this looks like this. 2 smooth rational curves meeting at 2 points. So that's the picture in the case K equals 1. In the case K bigger or equal than 2, this new curve class gives rise to a new section of the elliptic vibration. So let me show a very easy picture of what is more or less going on. Again, we have many smooth fibers. We have some nodes. In the very general case, all the fibers are irreducible, but the important thing is that we have, well, the first section, the 0 section, and we have a new section. Let me call it S. And this K here takes care of the intersection of this new section with the 0 section. It's precisely the intersection number is K minus 2. So as K grows, we're basically considering K3 surfaces admitting so elliptic vibrations with more than one section, and this new section intersects the 0 section with many, many, many more points. So that's the geometric interpretation of these moduli spaces. So of the objects of these moduli spaces. And finally, we come to our results. So the first theorem takes care of general type argument, and we prove that this moduli space is of general type if K is big enough. In this case, big enough means at least 220. And we have information about smaller values of k. And on the other side of the spectrum, we have theorem 2 that says that these moduli spaces are unirational for small values of k. And we actually have a lot of cases in which these moduli spaces are unirational. In particular, it holds for k smaller or equal than 34. The biggest value for which we are able to show unirationality is 97. So numbers are not so important. What I want to stress is that we get a picture that is very similar to the case of the moduli space F2D studied by Gritsenko, Ulek, and Sankaran, and other people. So the situation is that for small values of the determinant of the lattice, these moduli spaces are unirational, whatever small means. And for big values, they are general type. But unfortunately, in both situations, there's a gap in between, and we have no information at all about the moduli spaces in this gap here. And unfortunately, in our case, it's a big gap, like 100 values of k. And current, I mean, we're trying to improve, especially this second theorem. And we recently made an improvement. We proved that one of the hardest values for us was k equals 11. I hope I'll say 2 words at the end about it. But we were able to improve this result by, and I'll show you the methods and how we can improve this. So that's basically the introduction. And if there are any questions, I'd be happy to answer them. Okay, so maybe I get this remaining 8 minutes to talk a little bit about this second theorem, because the proof is very concrete. And so I'd like to give a couple of examples of how we prove that these moduli spaces are unirational. So the main idea is kind of straightforward. We want to find explicit projective models for these K3 surfaces. And this would give rise to rational parameter spaces. And would prove the unirationality of these moduli spaces. And for K3 surfaces, we have a variety of projective models we can choose from. And we can construct them as Weierstrass fibrations. We can construct them as double covers of certain rational surfaces. But the method that solves the most number of cases for us is K3 surfaces in some projective space containing a pair of extra curves. The idea is that if we consider a K3 surface in Pn, there will be the hyperplane class, but our neuron severity has at least 3 classes. And we want these 2 new classes to be defined by very easy curves. That's the idea. So let me give you one example that is, this was the example that led us to this theorem. So the easiest example, and then we try to generalize this approach. So we want to prove that this moduli space M20 is unirational. And we want to find a projective model. What I claim is that a general U plus minus 20 polarized K3 surface can be realized in the following way. We take a quartic surface in P3 that contains 2 disjoint lines. So how do I come up with this projective model? Well, this is purely lattice theoretic. So theory of lattices says that we have the following isomorphism of lattices. And we like a lot this matrix on the left because we have a vector of norm 4. This suggests that the K3 surface should live inside P3 as a quartic surface. And we have 2 extra curve classes of norm -2. So this means that they should be rational curves. They have 0 intersection numbers, so they should be disjoint. And they should intersect the hyperplane section at 1 point. So they should be lines. So our intuition says that, not our intuition, but this isometry of lattices shows that there should be, the general element should be a quartic surface in P3 containing 2 disjoint lines. And this is indeed the case. So first of all, this is kind of a remark, but I think it's nice. So we said that these K3 surfaces are elliptic. So they emit an elliptic vibration. But how do you see an elliptic vibration on such quartics? Well, it's standard, but I think it's very nice. So we start with a quartic surface X containing a certain line, L1. And what we do is consider the pencil of hyperplanes passing through this line. And as the pencil moves, it intersects the quartic surface in a quartic plane curve. But of course, there's a fixed line. So the residual curve will be of degree 3. So it will be a plane cubic, and so it will be an elliptic curve. And this defines a genus 1 vibration. But remember that there exists a second disjoint line, L2. This will intersect every hyperplane section at one point because it's a line, and it does not intersect the first line. So it will have to intersect the residual cubics. And so this is a section of the elliptic vibration. So this is kind of the geometric interpretation of this lattice isomorphism. And so now that we have this projective model, we just have to parameterize these surfaces. So first of all, we parameterize the lines, the disjoint lines. And that's easy because up to isomorphism of P3, we can just put the lines wherever we want. For instance, we fix the following two disjoint lines. And then our parameter space is just the set of quartic surfaces in P3 that contain these two curves. And well, that's clearly a rational space. And it's just the following projective space here of quartic surfaces containing these two lines. So this shows that the moduli space M20 is unirational because we have found an explicit parametrization of its objects. And so let me conclude by saying a couple of words of how we expand this strategy. The idea is very, very similar in the general case. It's just we need to be more careful. So first step is we want to find a suitable projective model. And this just means finding a suitable lattice isomorphism like this. We want to write our lattice U plus minus 2K as a certain nice 3x3 matrix where the intersection numbers are kind of, we expect what it should be. And so we expect that we could realize our K3 surfaces are, let's say, some complete intersection in some projective space containing a suitable pair of curves. Then how do we actually parameterize them? So first of all, we parameterize the pair of curves. So what we have is we want to parameterize all the curves in a certain projective space of fixed genus, degree, and intersection number. And that's not so hard. We use iterated Hilbert schemes, and since we only ask our curves to be elliptic curves or rational curves, these parameter spaces come up to be unirational. And as soon as we have successfully parameterized pair of curves, we can consider the following incidence diagram. So H parameterizes pair of curves with the properties that we want. And then we consider the following parameter space I of K3 surfaces X, so of complete intersections, let's say, in projective space containing this pair of curves. And well, that's very close to the end because, okay, we have chosen this H to be unirational. And we show this projection pi2 to be generically a projective bundle. So this says that also I is unirational. And well, if we prove that this pi1 map is dominant, we're done because we would have found a dominant rational map from I, which is unirational, to our moduli space. And well, clearly the map pi1 is only defined over the smooth quartics or smooth complete intersection X here. So what we need to do is actually we need to show, in order to show that the map is dominant, we need to show that there exists at least one smooth element in I. Because as soon as there's one, well, being smooth is an open condition, and so the image will be dense because M2K is irreducible. But it's, I would say, non-trivial to find one explicit example. And it's absolutely crucial that we were able to find one explicit smooth example, because if we don't, this map pi1 could be the empty map. I could only parameterize things that are not K3 surfaces. And this unfortunately happens a lot, but in all the cases that I listed before, we're actually able to find projective models and at least one smooth example that shows finally unirationality of this moduli space. And yeah, I wanted to talk a little bit about these recent developments because we're able to prove unirationality using different methods by looking at projective models in bigger projective spaces, in Grassmannians. But I think my time is up. And so I want to thank you for your attention, and I'll be very happy if there are questions.
Okay, so let's thank the speaker.